Hello, everybody. I'm Lup from sunny Singapore. I used to teach IoT, Internet of Things, in school. Today, I'm still in IoT education, but instead of teaching in the classroom, I write educational articles about IoT. I joined the Apache NuttX Project Management Committee about a year ago, and that's the topic of my presentation today. If you'd like to download the presentation slides, please head over to this link, lutyuan.github.io/nutx. That's the letter L, not the digit 1. My presentation, transcript, articles, and source code are available at that link. Apache NuttX is a real-time operating system. Works like a tiny version of Linux, but a lot smaller, a lot simpler. NuttX runs on many kinds of devices, from 8-bit to 64-bit devices, ARM and RISC-V, but not on a smartphone yet. Our smartphones are incredibly complex gadgets, super mysterious. Nobody really understands what's inside. What if we could boot NuttX on our phones to understand how our phones work? That would be the awesome way to learn the internals of a modern smartphone. But most phones are locked down, difficult to hack. Try hacking an iPhone. So we take a phone that was created for hacking. PinePhone is a remarkable 4G smartphone, assembled with off-the-shelf components, designed for mobile Linux. Inside is the all-winner A64 SoC, system on a chip, that runs 4 cores of ARM Cortex-A53. Yep, it's a 64-bit CPU. The components are surprisingly familiar. LCD display, touch panel, display controller, LTE modem by QuickTel, Wi-Fi and Bluetooth by Realtek, MPU 6050 accelerometer. The components are soft off the shelf, which makes PinePhone easier for learning and porting NuttX. To make sure we don't mess up people's phones, we boot NuttX on a micro SD card without touching the internal storage. No installation required. How exactly do we boot NuttX on a smartphone? Well, all we need is a PinePhone and a micro SD card. We download the NuttX image, copy it to a micro SD card, insert the micro SD card into PinePhone, power up, and that's it. NuttX begins to run on our smartphone. No fuss, no installation. So how did we get NuttX running on a smartphone? We took 1 whole year to build out NuttX for PinePhone. I shall explain the entire development process and the things that we can learn from NuttX on PinePhone. So PinePhone works like a normal phone, like an old iPhone 5S, which is also 64-bit ARM. All the components here are just simpler, affordable ones. So how shall we study the smartphone internals with NuttX? We begin with the most complex component, the LCD touchscreen that is connected on MIPI DSI. That's the display serial interface. Now, my background is in IoT microcontrollers. I'm familiar with SPI and ST7789 displays. But smartphone displays are overwhelmingly sophisticated. Inside the all-winner A64 chip is a display engine that renders pixels and pushes them to the LCD display over the display serial interface. Making this work with NuttX was a highly educational exercise. Thankfully, we didn't need to build all the drivers. NuttX provides some drivers like the frame buffer interface. that makes graphics rendering a little easier. Most of this isn't well documented, so we created quick prototypes of the display drivers in the Zig programming language. Zig is safer. It has runtime checks, so we don't run into bad pointers inside our prototype driver. When everything has tested okay, we converted the prototype drivers from Zig to C, which is not that hard since they are similar languages. Now, if we're doing all this work to teach the internals of a smartphone, we better make sure that everything is documented, which is why we wrote a stack of articles with whimsical sketches like these to explain what's really happening inside our phones. I can't imagine how else we could explain this intricate process, like turning on the display backlight, starting the timing controller, switching on the power, programming the display serial interface to push pixels to the display physical layer. Don't forget the frame buffer in RAM and the display engine. Hopefully our learners will understand a little better how our smartphones are pushing pixels to the display, together with the NuttX source code that we have thoroughly documented. Now, our smartphone isn't really so smart unless it accepts touch input. In spite of the missing documentation, we managed to create the NuttX driver for the touch panel, and we filled in the missing docs. Learners who are familiar with microcontrollers might find it fascinating that these touch panels will talk over a simple protocol like I2C. Now we need a way to write touchscreen applications like the ones we see in app stores, which brings us to an interesting problem. NuttX is a real-time operating system created for embedded devices, simple and easy to learn. But NuttX is not a general-purpose operating system like Linux, with its X11, GTK, Qt, SDL, and other graphical toolkits. So we borrowed something from the embedded world, LVGL, the popular graphics library for embedded devices. LVGL isn't something we normally use to write a smartphone app, but it works. Here are two demo apps that are bundled with the LVGL library. At the left is a forms-based app, at the right is a music player app. For those of us familiar with LVGL library, typically we see these LVGL demo apps running on a microcontroller. This is probably the first time that anybody has attempted to run the demo apps on a smartphone. We see that they work great with NuttX on PinePhone. Quick, smooth, responsive. And this is the LVGL terminal app that we created for NuttX. It runs NuttX commands in the NuttX shell. It looks a bit like Linux. These demos were created by calling the LVGL library in C programs, which might be intimidating for new learners. Let's talk about it. Since we are targeting education and learners, can we make LVGL apps easier to write? Something simpler than C without scary pointers. Something that has a safety net, a safety harness that will catch us if we fall into runtime problems. Once again, the Zig programming language. Zig works well with C, so importing LVGL types and functions into Zig is a piece of cake. Zig will check for null pointers and other runtime problems that we commonly miss, so our LVGL app will become safer. Zig can infer the missing types from our code, so there's less repetition and clutter in our code. Easier to focus. Zig will even automatically convert a program from C to Zig, which makes a good reference for studying the nuances between C and Zig. When we compare the C and the Zig versions of our LVGL app, yep, the Zig version looks simpler. Less repetition, less clutter. Yet Zig is actually doing more behind the scenes, like watching out for null pointers, underflow, overflow, array out of bounds. If something goes wrong at runtime, Zig will halt our program with a panic message and show a helpful stack trace. Let us take a peek at our Zig code. We no longer specify the LVGL types like for screen and label. Zig infers the LVGL types for us. Our code looks less cluttered now. Notice that we use try when calling the LVGL functions. This is how we handle errors in Zig. If any of these functions return an error, the execution stops and the error is returned to the caller. That is why we specify the return type with a bang or exclamation point. It means that this function might return an error. Nice tidy way to handle errors. The rest of the code looks similar to C, except that we move label to the front so that it appears more object-like. ++ is for string concatenation, but it works only for constant strings at compile time, so it is safe. That was a quick overview of Zig. Now there's a problem with smartphone apps. We need an actual smartphone to test the smartphone app. What if we could test smartphone apps in a web browser? That would be incredibly helpful for learners. We have Zig, and Zig compiles to WebAssembly. So yes, we can run our apps in the web browser. Here is an app created in Zig that runs in the web browser and the real PinePhone. This is great for learners because we can tweak and test our app in a web browser before testing on an actual phone. And a web browser is convenient for sharing and collaborating on our apps. Maybe someday we'll even allow apps to be created directly inside the web browser by dragging and dropping user interface controls. It looks messy, but this is how it works. We compile the LVGL library from C to WebAssembly with the Zig compiler, which works because inside the Zig compiler is a CLang compiler. Then we integrate LVGL to the web browser with some glue code in Zig and JavaScript. This is for rendering LVGL graphics. Then we handle the touch events, passing them from JavaScript to LVGL. This is a fun experiment that might change the way we write smartphone apps. What makes a smartphone a phone? Let us not forget the 4G LTE modem that is inside PinePhone. This QuickTel LTE modem works like any typical LTE modem. It uses AT commands, which works well with NuttX for making phone calls and sending SMS text messages. Here is a fun fact about smartphones. There is an entire computer inside our smartphone. Inside the LTE modem that talks to the 4G network, we have an ARM CPU with serial ports, digital audio, USB, wireless, and GPS. This is a computer in itself. Fantastic opportunity for learning something totally new inside a smartphone. Here we see the AT commands sent by NuttX to the LTE modem for making a phone call. Yep, NuttX works okay for making phone calls, though the audio part is not quite there yet. And here are the AT commands for sending an SMS text message. This is just hilarious. Inside a smartphone, we are still sending the same AT commands that have been around since 1981. That is 42 years ago. Now with NuttX, our learners can truly appreciate the power of AT commands inside our smartphones. Remember the feature phones from 1999? The plain and simple Nokia phones that will make phone calls and send text messages only? We are almost ready to turn NuttX into a feature phone. We have the feature phone app, created with Zig and LVGL library, tested in a web browser, and running on PinePhone. Outgoing phone calls and text messages over 4G are working okay. Now we need to work on the incoming phone calls, text messages, and digital audio. Remember the Zig app we saw earlier, running in a web browser? Here is the same app running on a real PinePhone. This might sound strange and counterintuitive. Why are we turning a smartphone into a feature phone? Like regressing back to the past, going retro. Well, when we structure this as a learning experience, it actually makes a lot of sense. A smartphone is a phone after all. Hence, we start with the basics, making phone calls, sending text messages. Then the rest will follow naturally. Mobile networking, smartphone apps. It's amazing that learners will be able to understand the inner workings of phone calls and text messages from inside out, and maybe inspire our learners to create their own feature phones. Yet, we have plenty of room to grow for advanced learners. They can build the Bluetooth, Wi-Fi, and mobile data drivers from NuttX. I am particularly fond of LoRa, that is the long-range, low-power, low-bandwidth wireless radio network. PinePhone has a back cover with a LoRa chip inside. Absolutely brilliant. Would be great to have LoRa mesh networking on a smartphone, an alternative peer-to-peer wireless comms network. But a modern smartphone has so many things inside. How close are we in getting everything to work with NuttX? This is our roadmap for NuttX on PinePhone. The features we have built, the features that we are going to build, and the features that we built halfway through. The touchscreen works great, even with touchscreen apps. Our support for PinePhone sensors is a little spotty. We have some glaring gaps in our roadmap: USB, networking, core security features. That is because we are a very tiny team building NuttX on PinePhone. Let's talk about the sensors on PinePhone and why they are especially interesting for embedded learners. Those of us familiar with embedded development, Arduino and IoT microcontrollers, quite often we connect sensors to our microcontroller boards so we can program and test the sensors, plug in, plug out on a breadboard again and again. With a smartphone, there's no need to connect sensors. A whole bunch of sensors are already inside. Sensors for gyroscope, accelerometer, temperature, magnetometer, light, proximity, even GPS. It's much easier for learning and experimenting. Not all drivers are available in NuttX today, but it will be an awesome educational exercise for students to contribute the missing NuttX drivers. Now we step out from smartphone sensors and head into something more challenging for learners: USB in a smartphone. USB is needed by the LTE modem for GPS to work because GPS talks over the USB interface. We are building the USB EHCI driver, that is the Enhanced Host Controller Interface. EHCI supports only USB host mode, not USB device mode. For USB device mode, we need the USB OTG, on-the-go driver, for the Mental Graphics USB controller, which we haven't started. There are many things that we take for granted in a modern smartphone. Multiprocessing for multiple CPUs, security for memory and apps, graphical processing unit. For advanced learners, this could be a serious opportunity for research and development. We have plenty of features in our smartphone roadmap. It would be great if we had a smartphone emulator for testing all these features. We might have a solution for that. We'll explain in a while. Now imagine a classroom of students learning about smartphone internals by booting NuttX on the phone. Are we ready to teach NuttX in schools? The code that we have seen today is already available in the NuttX mainline repository, open source, free to access on GitHub, contributed by the fantastic NuttX community. Now, to teach NuttX in a classroom, we need textbooks, right? Well, we have a huge stack of 24 articles written over the past year. Imagine a thick textbook on NuttX with 24 chapters inside, covering all the topics we discussed today: touchscreen, smartphone apps, ZIG programming, LTE modem, sensors, USB, even a step-by-step guide for submitting a pull request for NuttX. Our textbook for NuttX should be sufficient for self-study on smartphone internals. Sometimes it's helpful to have a smartphone emulator for experimenting and automated testing. We are building a PinePhone emulator with Unicorn emulator, which is a programmable variant of QEMU. Here is something fun we created with Unicorn emulator, a clickable call graph that visualizes the call flow in NuttX. Have we ever wondered what happens when an operating system boots on our computer? Thanks to Unicorn emulator, we can visualize everything that happens when NuttX boots on our smartphone. We are building a PinePhone emulator with Unicorn emulator, which is a programmable variant of QEMU. Unicorn emulates the entire startup process of NuttX, and that is how we render the call graph that visualizes the call flow at NuttX startup. This is interactive too, so when we click on a box in the call graph, it jumps to the NuttX source code. This is a fun new way to use software emulation for smartphone education. ARM64 is an extremely popular platform today for all kinds of gadgets. Just follow the exact same steps we meticulously documented today, and NuttX will probably run on any ARM64 device: iPhone, Samsung phones, tablets, laptops, even gaming handhelds. Now we have a fresh new opportunity to teach a new computing architecture from scratch, the 64-bit RISC-V architecture. Now sadly there isn't a RISC-V phone yet, thus we'll port NuttX to a RISC-V tablet instead, the PinePhone 5. We begin by porting NuttX to the Star64 single-board computer, which runs on the same RISC-V SoC as PinePhone 5, the Star 5 JH7110 SoC. Today, NuttX mainline officially supports the Star64 JH7110 single-board computer. NuttX also boots OK on another single-board computer, the Star 5 Vision 5 2, because it runs on the same RISC-V SoC, Star 5 JH7110. Right now, NuttX on Star64 is a bare-bones port. We are creating the NuttX drivers for I2C, PMIC, and HDMI. We mapped out what needs to be done for the HDMI driver, and it looks seriously complicated. Fortunately, we can reuse some of the existing NuttX drivers. Star64 runs on the same I2C hardware as S-Presence CXD5602, so we shall borrow the S-Presence I2C driver from NuttX. I find this quite surprising actually, that 64-bit RISC-V SoCs are running on the same IP blocks as 32-bit ARM SoCs. In this case, it's the designware IP block for I2C. This is the lesson that we have learned. We might not need to create NuttX drivers from scratch. even for newer 64-bit SoCs. Just snoop around the existing NuttX drivers, we might find a driver for the same old IP block. Thanks to the awesome work by Anna Bonilla, NuttX mainline also supports PinePhone Pro. This is the next generation of PinePhone running on the Rockchip RK3399 SoC. Thus today, we have two smartphones that run NuttX, PinePhone and PinePhone Pro. NuttX on PinePhone Pro is a bare-bones port, now adding support for GPIO, I2C, and display driver. We dug around and discovered that Rockchip GPIO might actually work with the NuttX driver for PHY62XX GPIO. So it definitely helps to shop around and look for a matching NuttX driver. Something fascinating has happened over the past year. Let us call it NuttX Next Gen. Traditionally, NuttX runs on 32-bit microcontrollers with tiny displays. But over the past year, NuttX has evolved to run on 64-bit smartphones and single-board computers, like PinePhone, PinePhone Pro, STAR64JH7110, and IMX8 Quad Max. Yes, these gadgets are 64 devices with larger screens, but there is a much deeper significance. Let me explain. Look at the 64-bit SoCs that NuttX supports today. Allwinner A64, Rockchip RK3399, NXP IMX8, STAR5JH7110. What is in common? All these are really popular consumer SoCs. They are used in many consumer gadgets. Allwinner A64 is used in many single-board computers, a few laptops, and even a handheld gaming console. What if we run NuttX on all these gadgets? Retro gaming on NuttX sounds really fun. Rockchip RK3399 runs NuttX on PinePhone Pro. What if we tweak NuttX to run on these single-board computers, laptops, tablet, and handheld gaming console? Rockchip is also packaged as an SOM, System on Module, that is compatible with the Compute Module 4 by Raspberry Pi, which means NuttX can be embedded in an SOM for all kinds of gadgets. NXP IMX8 is especially interesting because it powers another Linux phone, the Librem 5 phone by Purism. This might become the third smartphone supported by NuttX. We cross over to the world of RISC-V. The STAR5JH7110 SoC is starting to appear in many devices. Today, NuttX boots on these single-board computers, STAR64, Vision 5.2, and probably Milk 5 Mars. We hope to port NuttX to the PineTab 5 tablet. JH7110 SoC also comes in an SOM, System on Module form factor. That's the Mars CM. This sounds like an impressive strategy for spreading NuttX across many consumer devices. Smartphones, single-board computers, tablets, laptops, system on modules, even gaming handhelds. What is your favorite flavor of pie? Banana? Orange? Maybe rock flavor? NuttX will probably boot on your flavor of pie. But we have a major problem with these devices. Open source drivers are very rare for these consumer SoCs, and they lack proper documentation. We are slowly building up the NuttX support for these SoCs, bit by bit, driver by driver. Yes, it feels a little tedious, a little painful. That is why we seek your contribution to fill in the missing NuttX drivers. I think it is awesome that people will be learning more about the inner workings of their smart gadgets by booting NuttX on their smartphones and single-board computers. Our presentation today has explained how exactly we created the NuttX drivers for PinePhone. Hopefully, we can follow the exact same steps to create the missing NuttX drivers for the next generation of NuttX devices. Coming back to PinePhone, everything that we have covered today is documented in these articles: display serial interface, display engine, LCD panel, frame buffer, touch panel, LVGL, WebAssembly, and our feature phone app. Wait, there's more. We have articles about the PinePhone accelerometer, LTE modem, GPIO, UART, USB, power management, interrupts, and PinePhone emulator. We are now writing a new stack of articles about Star64 GH7110, the new RISC-V single-board computer. Check out the Star64 articles here. Apache NuttX on PinePhone has been an incredibly rewarding journey, thanks to the awesome NuttX and PINE64 communities. We have seen so many educational opportunities today. I hope to do lots more with Apache NuttX in education. And we welcome your contribution to the Apache NuttX project. Thank you.